Okay, so in this experiment, we're going to investigate uncertainty in a reading and a measurement. And we'll be finding out which gives us the biggest uncertainty. We will also consider how to deal with uncertainty when you calculate a change in mass or a change in length. I'm going to use the potato experiment that we used in required practical 3. I'm going to take 3 identical cylindrical tubes at about 3 centimetres or 30 millimetres long. Then I will weigh their mass and I'll measure their length. Then what I'll do is I'll put them in a 1 molar concentration of salt solution, leave them for 20 minutes, and then I'll re-weigh them and re-measure their length. So here I am, just ensuring that my potato tubes are aligned, and I'm cutting them to 3 centimetres, but of course afterwards I'll individually measure each one to make sure that it's correct. Okay, we need to make sure, of course, that your boiling tube actually fits in your test tube rack, so I'll go and get another one. Okay, so now I've got a boiling tube where my boiling tubes will fit. I'm going to take each potato cylinder, roll it gently on some paper tissue to ensure that any excess moisture is removed before I measure its mass. I'm just labelling my boiling tubes there, A, B and C. Okay, so now I need to organise my digital balance. I'm doing that by adjusting the feet on the bottom, and I want to make sure that the air bubble is centred. And the only way I can do that is by looking from it from an aerial position. And as you do that, you'll see it pop into the centre, and that means that the digital balance is level and will therefore measure the mass accurately. So here to the left of the digital display, you can see a little air bubble, and when you move over the top of it, you can see that the air bubble is in the middle. I'm now going to measure the mass of each of the potato tubes. I'm going to record the result straight onto my worksheet, and then of course I'm going to measure the length with the ruler. Of course, with the digital balance, just a reminder that that's a reading because we just get one judgment made, whereas when we measure with a ruler, it's a measurement because we use 2 judgments. Okay, I need to make my 100 mils of sodium chloride solution, which is 1 molar. Well, if I was making a litre of it, which would be 1,000 millilitres, I would use 58.5 grams of sodium chloride. But I only want 100 mils. So I need to divide 58.5 by 10, because that's what I've done when I moved from 1,000 mils to 100 mils. So in actual fact, I'm going to be adding 5.85 grams of salt into 100 mils to make my 1 molar 100 ml sodium chloride solution. I place the weighing boat on the digital balance and press tare to 0 it. And there's my calculations there for how I made my solution. And I weigh 5.85 grams of sodium chloride. I then empty that into my 100 mils of water, and I'm going to swirl that so that the salt dissolves. I then add about 30 mils of the salt solution to each potato chip, and then I start my timer. I'm going to time for 20 minutes. Following the 20-minute time period, I'm going to retrieve my potato cylinders. I'm going to roll them on paper towel again. I'm going to weigh them and I'm going to measure them. And I'm going to record all of this on my worksheet. I then calculate the mean change in mass, and I calculate the mean change in length. And of course, I don't need those results to know the uncertainty for the instruments I've used, because they are what they are. They depend on the resolution of the instrument and they remain the same. However, I may want to apply them to the results I have, and that's when I calculate the percentage uncertainty. But before I calculate my percentage uncertainty, I have to remember that I had uncertainty before and I have uncertainty after. So I have to double it. So in the case of the reading, I will just have the 1 uncertainty that I'll double. In case of the measurement, I will have 2 uncertainties that I will then double. Measuring to 1/100th of a gram is quite a small resolution, and so we're going to get quite a low uncertainty with that. While measuring changes in length over such small changes, a millimetre is actually quite a large resolution to use. And so that's why we've got such a massive uncertainty to apply to our results. Okay, let's go over that one more time. We measured our potato before the experiment. We found in this case, for instance, it was 2 millimetres long. A millimetre was the resolution of this instrument. Even if the potato had measured 1.5 along here, we would have said it was 2 millimetres. Even if the potato had measured 2.4, we still would have read it as 2 millimetres because that is the resolution of our instrument. So we have an uncertainty. We have from 1.5 to 2.49 an uncertainty. Because we have done the same at the beginning of the potato where we've lined up the 0, we've also got the same uncertainty. So here we've got an uncertainty of plus or minus 0.5 millimetre. And here we've got an uncertainty of plus or minus 0.5 millimetre, giving us a total uncertainty of 1 millimetre. But then we calculate the change in the length of the potato. And we do the whole thing again. So we end up with another uncertainty there and another uncertainty there. So in total, my uncertainty for the change in length of that potato is 2 millimetres because I need to add all of these uncertainties together. The uncertainty of the digital balance is slightly different. And that's because the digital balance takes a reading and not a measurement. What do we mean by that? Well, a reading, we can rest assured that 0 doesn't need any judgment from us because 0 has been calibrated by the manufacturer. So when I measure the mass of the potato, all I'm measuring it to is the nearest resolution. And in this case, the resolution was to 0.01 of a gram. Now, we can say that even if it had been 0.005, it would have shown us this on the digital balance. Even if it had been 0.014999, it would have shown us this on the digital balance. So either side of that, we've got a resolution of, we've got an uncertainty of plus or minus 0.005. So with the digital balance, which takes a reading, it's got a resolution of 0.01 of a gram, and it therefore has an uncertainty of 0.005 of a gram, which is half of this. So therefore, if we measure the mass before and we measure the mass after, we've got two uncertainties and we need to add those together. So therefore, mass before and the mass after gives an uncertainty of 0.01 grams. But that uncertainty just is what it is. That uncertainty stays with that digital balance no matter what mass you're weighing on it. So to make that uncertainty relate to the mass that you're using, we use percentage uncertainty. And to calculate that, what we're going to do is we take our uncertainty and we divide it by, and we times it by 100. So in this case, our value would be the change in mass. And that's what we're applying our uncertainty to. Just like we would do if we were looking at the change in length. The uncertainty stays with that ruler. It's based on the smallest resolution. So of course, to make that uncertainty from that ruler match what you're measuring in relation to what you're measuring, what you're going to do is work out the percentage uncertainty, and that's when we use this formula here. So it would be the uncertainty divided by the value for your change in length times 100. And of course, in our experiments, when we've looked at the measurements, we've got 4 times plus or minus half the resolution. And when we looked at the reading from the digital balance, we've got 2 times plus or minus half the resolution.